Thanks, Tom. So right away when I started my lecture yesterday, I made a terrible mistake, which I need to correct. So after the lecture, I'm thinking back about it, of course, thinking, oh, that went pretty well. But then I realized I forgot to thank Veronica. I was thanking the organizers, I listed a bunch of people, and I forgot to thank Veronica. So somehow this happened. Veronica, I'm sorry.
No
Thank you.
problem.
And
You're welcome.
it reminded me a little bit of when you watch people give these Oscar speeches and they like are all flustered and they don't know. Thank all these people. And you might say, well, you knew you were lecturing at TASI for like 8 months. You could have, those Oscar winners, they just find out right then. But when the bright lights go on, everything goes out the window. So please forgive me. And now that the record is set straight, we can continue. So good. So yesterday we talked a bit about what it is that the Bootstrap is trying to do for AdS CFT among many possibilities. And today we're going to talk a bit about one of the tools in addressing some of those questions, which is the computation of 4-point functions in strongly coupled theories with bulk duals, both from the bulk side and from the boundary side. First, I want to start, though, just returning to this figure, which we had a little less time to discuss than I would have liked. And so I won't recapitulate everything that's in here because I think we got to some of the main features, but maybe I should just first ask if there are any questions people had lingering about the different regions of the spectrum of single trace operators in holographic theories and what each one represents.
Actually, I have maybe a very naive question. What's the meaning of delta gap if you have lighter modes?
So delta gap is...
Usually when I think of gap is that there are no massless particles and then the first mode has that energy.
Right, so here it is referring specifically to the dimension of the lightest single trace operator of spin greater than 2. So there's a gap in the single trace higher spin spectrum.
Okay, so you can have other excitations, but they have to be lower spin.
Yes, yes.
Okay, thank you.
Mm-hmm. Any other questions? Okay, good. So of course, this will be something that we, return to directly and indirectly throughout the lectures. So let me introduce just CFT 4-point functions, the constraints of conformal symmetry on them, what crossing symmetry is, and then we'll move on to how you compute them in the context of AdS CFT, and what you do with them. So I'm going to continue to call my local operators O in general, unless otherwise noted. So let's, for simplicity, consider a 4-point function of identical scalar primaries O. And using conformal symmetry, we can put this into the following form. There's some power law prefactor where delta is the dimension of O, times some function which I'm going to call A of conformally invariant cross ratios U and V, where U is defined as this particular ratio of the squared differences of distances, and V is a slightly different one. So conformal symmetry allows you to write a 4-point function in this way. The argument for why that is can be found in many places. For example, the TASI Bootstrap notes I referred to yesterday. And one can reparameterize these two, in general, complex cross ratios U and V in terms of complex variables Z and Z bar. That will be convenient. So let's do that. Here's the parameterization, which is very common. And so let's think of this as a function of Z and Z bar, which I like better. So if we think of the complex Z plane, you can use conformal symmetry to put an operator at 0, an operator at 1, an operator at infinity, and then the fourth operator can be thought of as sitting in this plane. Now, in Euclidean kinematic Z bar equals Z star, but they can be continued away from that to be separate, independent complex variables. We won't really need that for today, but you should know that. Okay, so we want to use the OPE to expand our correlator. And there are different channels in which to do this. So we can bring operators together in pairs in different ways. So for example, in what I'll call the S channel, we take U to 0, which is small z. And so here, A can be written as a sum over some intermediate operators phi that are being exchanged between our external operators, which I'm going to denote in this way in terms of the legs of my correlator. Right? So I have operators 1, 2, 3, and 4, and this operator phi is being exchanged in the middle, and we have a bunch of operators being exchanged that are inherited from the structure of the OPE between 1 and 2 on the one hand, and 3 and 4 on the other. And phi must appear in both. So multiplying whatever kinematic thing this is a product of OPE coefficients C1, 2, phi, C3, 4, 5. We can also do this in what I call the T channel, which is the V goes to 0 regime. In other words, Z goes to 1. And in this case, well, we're going to expand in the 1, 4 goes to 2, 3, because that's what makes V small, right? So we have some other sum over some other set of operators in general, a phi prime. 1, 4, 2, 3, phi prime in the middle, and now this, this combination of OPE coefficients. There's also a U-channel expansion around Z equals infinity. That's important for various things, but we won't need to talk about that today. So far I've written this as a sum over whatever operators appear in these OPEs, but we can use conformal symmetry even more to package the redundancy of conformal symmetry into what are called conformal blocks. So conformal blocks are defined by the sum of exchanges in some correlator from an entire conformal multiplet. And by conformal multiplet, I mean, well, the following. You have some primary O, which here I'm writing as a state, and we can act with that on that with the raising operators, a conformal group, namely the momentum P mu, any number of times and in many ways, in any way that we can contract the tensor indices, right? So these are all different descendants of the original primary O, ... And so this whole multiplet gets exchanged, and conformal symmetry actually relates the OPE coefficients of all these descendants to that of the primary. And as a result, you can once and for all determine the structure of these conformal blocks using conformal symmetry, and then restrict your sum in this decomposition to sums over primaries only, where the kinematic thing that is represented by these stick figures is the conformal block. So we write our 4-point function in this channel, the S channel. We can now restrict to primary phi, and then we have these phi exchanges, and here and elsewhere I'm going to start sometimes suppressing the actual OPE coefficients, although they're always sitting at these vertices. Okay, hope that's not confusing. It is customary. And so now this thing here is the conformal block. So it represents the exchange of phi, but also these derivatives of phi.
Eric,
Yes.
it seems like part of your screen is cut off.
Really?
Yeah. I wasn't, someone else missed it. The left part.
The left part.
Now it's good.
Really?
Yeah.
It was cut off for you also?
A little. Yeah, it was cut off for me also. But now it's fine.
That's bizarre. Okay. Let me know if it happens again. Sorry.
Sure.
Okay. So these conformal blocks are sometimes denoted G sub phi. And here and elsewhere, I'm suppressing the fact that we sum over different operators, and these operators come with dimensions delta and spins J or L. So everything's really a sum over spin and delta, right? So conformal block G sub phi, well, that depends on the dimension of phi and the spin quantum numbers. But once those are specified, given the external dimensions, the block is fixed. So what should be
to be clear, the block is a function of Z and Z bar, just as
yes, it is. Thank you. It is all of the dependence on Z and Z bar is in the block, right? So the OP coefficients are constants in this way of writing things, and all the Z and Z bar dependence is here, and the leading Z and Z bar dependence of the block, depends on the quantum numbers of the exchanged operator phi. And then as you expand this block in powers of Z and Z bar, the coefficients of the subsequent powers of Z and Z bar also depend on those quantum numbers. In even dimensions, there's a closed form for these conformal blocks, which is basically sums of products of hypergeometric functions. For odd dimensions, there is no closed form. Nevertheless, there are efficient approximations, many of them, in fact. So for one thing, there's a series expansion, which can just be worked out by hand, level by level, by using the structure of the conformal multiplet, but fortunately was worked out long ago by Dolan and Osborne in a closed form. It just can't be resummed. So for lots of purposes, the series expansion is just fine. There are also some recursion relations. There are integral representations, and conformal blocks obey what's known as the conformal Casimir equation, which is a second-order differential equation, which can be derived by noting that every state in the conformal multiplet has the same value of the conformal Casimir by definition of a Casimir, and writing the generators as differential operators, you can turn that fact into a differential equation, which is basically a hypergeometric type in the even dimensional case, but otherwise is just not. Okay, and so then there's more here. Good. So crossing symmetry is associativity of the OPE. So if we're looking at this 4-point function of O's, I can use the OPE in different ways. I can contract 2 and 3 and 1 and 4, or I could contract 1 and 2 and 3 and 4, or the third combination, which I didn't say. And so in terms of these different channel decompositions that I wrote earlier, this is just an equality between those decompositions. And the key point is that the blocks are not crossing symmetric. what the whole sum must be. So imposing this is powerful. And by that, I mean, if you imagine that you knew some of the data, say you know the spectrum of operators over which you're summing, but you don't know the OPE coefficients, then imposing crossing symmetry can help you determine them. Or if you know almost nothing about the operators being summed over even, maybe you just know that there's an identity operator in the fusion of the two identical operators O, which are on the outside, and you just want to know what else does there have to be, and that's all I know. Crossing symmetry can help answer that question for you too.
Can I ask a question?
Please.
I thought that when you want to use the OPE to simplify correlators, you can only do the OPE between two operators if there's no other operator inserted in between them, so that you can bring the one operator to the other. So I don't see any way in which you can possibly do all three of these OPE channels at once. Like probably at least in one or two of those ways of bringing operators together, you're gonna hit an operator insertion along the way. If you just think about 4 points in a plane or on the Riemann sphere.
Yeah, good. So each channel converges in a certain region, and crossing is useful when you equate two expansions that have overlapping region of convergence. So that's where you want to use a given crossing relation. But in different regions of the complex plane, you're allowed to do different things.
Okay, so each crossing relation only works for a certain subset of points.
Yeah. Mm-hmm.
Okay, thanks.
Sure. As I'll try to remark toward the very end, the crossing symmetry itself can be reformulated in a way which makes no reference to the blocks and really to the position dependence at all. What you're saying, the point you're bringing up is still relevant there, but you can almost just forget about the blocks. There are other formal issues with phrasing it that way. I'll try to say this at the end, and if I don't, then you can ask me the questions. But I'll try to explain what I mean.
Thank you.
Sure. Any other questions? Okay. So it's powerful. By now you've surely heard about this. There are lots of numerical studies, some of which are hinted at yesterday, and there is a lot of analytic progress being made too. More and more every day, I would say. I'm sure there's more to come. This isn't a talk about the Bootstrap just in the CFT context per se. So that of course, and has been the subject of an entire TASI lecture series. If you were to give, though, a lecture about the Bootstrap just strictly in the CFT context, you would have to point out what's known as the light cone bootstrap, which is one of the first and still most powerful analytic approaches to solving crossing in general CFTs. So let me just mention this. For your knowledge, and perhaps you can follow up on it if you like. The point of the light cone bootstrap is to solve crossing in the regime z much less than 1 minus z bar much less than 1. So you take small z, then you take z bar to 1, and then you solve crossing. This was done first in some papers at the end of 2012, one by Fitzpatrick et al. And one by Komogazzi and Zhiboyedov. I will give the references in this document on the wiki, which for those of you who didn't notice, I've put with some references and sort of a paragraph about the papers I referenced, how they fit into the general story that I was trying to tell yesterday. And I'll do that today, again, with every reference that I mentioned here, and maybe some others. Okay. Good, so they solved crossing in this regime, and suffice it to say for now that the main conclusion is that if you have operators O1 and O2 in your CFT, then the CFT also has an infinite tower of other operator. of other operators, which are primaries, which have dimensions delta equals delta 1 plus delta 2 plus 2n plus L, where L is the spin, plus some number over L to the d minus 2, and L becoming asymptotically large. So in other words, at asymptotically large spin, all CFTs look like they have this free Fock space of operators comprised of gluing other operators together to make composites. And the anomalous dimension is 1 over L to the d minus 2, where d is the dimension of the CFT, was computed. It was computed by using this method. And a whole systematic machinery for understanding this has been developed in the years since. Okay. This conclusion also generalizes. This is the simple version, the main punchline.
Are there more assumptions here? Because what about like rational CFTs in dimension 2?
Yeah, so this is for dimension greater than 2. Thank you. And actually, in the 4th lecture, I hope to come back to that, but it's important that d is greater than 2. And just to give a snippet of why, a key point here is that there is a gap in twist between the identity operator and the next lowest twist operator. Twist is defined as the dimension minus the spin. And in 2 dimensions, the holomorphic stress tensor and any of its composites have 0 twist. And so there is no gap between the vacuum and the next operator. But in d dimensions, the stress tensor has twist d minus 2. And indeed, this d minus 2 over here is this d minus 2 over here. Okay. Okay. So any other questions? This concludes the kind of just CFT background part before we transition to large N correlators. Okay, good. So we're going to study correlators at large N, and especially in strongly coupled theories. And this means, from the holographic point of view, computing Witten diagrams, which Mukund introduced in his lectures. And we want to develop the 1 over N, or the 1 over C expansion of these correlators and ask what kind of information do they contain? What are we really computing when we compute Witten diagrams? And what are the essential data that characterize a large N CFT of the holographic type? Okay. I'm going to try to use C, but sometimes you see conventions where C is just taken to be parameterized by some new fictional parameter n. Usually the canonical scaling people like to choose is n squared because that's what it is in gauge theories. Okay, so that's just a side remark related to my sort of clumsiness about using n and c yesterday. Often people just say we're going to define c as n squared and then we can talk about n and c. Okay, they're just something to look out for when you look in papers. Okay. Good. So what are Witten diagrams? Witten diagrams are just AdS Feynman diagrams. I have a joke about these. So Witten's insight was just to take a Feynman diagram and draw a circle around it. And that's why he has a new thing now. So good. So let's just draw some random AdS Feynman diagrams. So here's a simple one. Here's a slightly more complicated one. Here's a slightly more complicated one. Here's an even more complicated one. ... I'm restricting to 4 points just because that's what we'll do. Of course, you could draw endpoint diagrams. Those have been somewhat studied, but definitely less so. And in the Bootstrap at large, endpoint functions have been less studied than 4-point functions. So this diagram, this first one on the left, is a disconnected diagram. it's just free propagation. And so in the 1/c counting, this would just be order C to the 0, where we're just taking products of 2-point functions, and I'm imagining a normalization where 2-point functions of these single trace operators are normalized to be of order C to the 0. Now, these guys here are connected free-level diagrams. And so they would contribute at order 1/c in the large C expansion of some 4-point function. This, of course, is a one-loop diagram. This would contribute at order 1/c squared. And in making these statements, I'm assuming that all the vertices, the interactions, scale with canonical powers of 1/c or 1/√c. That kind of assumption is often baked into arguments people make about the space of holographic CFTs, but I should say it's not something that has to be the case for every family of large C theories. But you want to think of there being some bulk action where there's a 1/g Newton out front, and all of the interaction vertices that are in the Lagrangian just have order 1 factors in units of g Newton. Okay. And so then you get this kind of expansion. This is the case for all controlled constructions.
So, sorry, you are saying the 3-point vertex are 1/√c, but the 4-point vertex is 1/c, right?
Yes. Yes.
Okay.
In general, the endpoint vertex is, well, every time you add an n, you add a 1/√c, whatever that scaling is. Yeah. Yeah. Okay. So let's start with the C to the 0 disconnected diagrams. And then we'll talk about the connected diagrams. The loops, maybe we'll talk about tomorrow.
Is there intuition for this? Like why for endpoint vertex, it should be like 1/c to the n/2 or?
Well, you can make an argument based on, so once you have the kind of action that I articulated before, you can see what types of factors vertices and propagators carry, and then just sort of algorithmically determine this.
I see. Yeah.
The question is really whether an action has to have that kind of scaling. But once it does, then what I said is not too hard to establish.
Okay.
Just a question about that assumption. So it's a little bit odd to think that all the interaction strengths scale in the bulk theory, scale with G Newton. Is there a reason why you're making that assumption?
Let me give you 2 reasons. So first of all, I agree that it's not for sure that always has to be the case. But first of all, in controlled compactifications in the context of string theory, or really supergravity, that's what happens. And okay, maybe you say lamppost, and fine. But then there was a recent, in this recent paper about the sharp boundaries for the swampland, and then the AdS version of that by Karen Huo et al. That I referred to yesterday, they show in a highly symmetric setting, namely that of n=4 amplitudes, that the types of constraints they work with, which are essentially a form of causality and crossing, show you that in that setting, all the interactions, the quartic interactions, do have to scale with G Newton. So they're assuming there's some EFT, which is weakly coupled up to some massive scale, which is well below the Planck scale. And they assume some other sort of mild things. And out from this pops a bound on these 4-point functions, which has a G Newton built into it necessarily. So all of the interactions necessarily scale in the way that I've described when you have n=4 supersymmetry. And that's on pretty general grounds. That's an independent kind of argument. And one might imagine that something like that would be possible to show more generally, or at least maybe with a little bit of supersymmetry or something. But
cool. Thanks.
Sure. That can be found in like a later section of their swampland paper, maybe the second to last section. Okay. So good. So the disconnected diagram, well, if you were computing at order c to the 0, a correlator, well, here I've just drawn one channel, right? But we really have diagrams in all 3 channels. So 3, 4, and then we'd have, with the same numbering, we'd have this, and then the U channel one, which is always annoying to draw. And so it's clear that, right, this first diagram just gives a 1 over x12, x34 to the 2 delta, just products of 2-point functions. And then the obvious permutations hold here. And so just extracting the overall power law factor involving the x's, the corresponding 4-point function is just 1 plus z bar over 1 minus z, 1 minus z bar, all to the delta, plus z bar to the delta, where each of these terms corresponds to the graph above it. So this is the answer. It's crossing symmetric by construction, of course, because the holographic dictionary instructs you to sum explicitly over all the channels. And so if you decompose this into conformal blocks, well, what will you get? So let's decompose it in the S channel, which is small z. So first we get the identity, and then we're going to get 2 infinite sums, sum over some number n, and sum over L, of double trace exchanges. So these operators OO and comma L are these double trace composites. And this is a shorthand for a sandwiching of a bunch of derivatives by 2 O's. So n is like a center of mass kind of quantum number in the bulk, which counts how many powers of del squared you have. And then L counts the spin, and that's just how many open derivatives you have. And these act both ways, and you subtract traces to make it primary and so on. But O, n comma L is a shorthand for these double trace composites. They have dimension 2 delta plus 2n plus L. And at this order, that's the exact dimension, because this is just free fields in the bulk. This whole disconnected construction, where there are no interactions, is known as generalized free fields. So everything here is just the 4-point function of generalized free fields. And it's called that just because in CFT terms, you have some crossing symmetric correlator where delta can be an arbitrary parameter, but in AdS, you literally have a free elementary field. So generalized free fields.
Can I ask a question?
Yes,
I'm
please.
just a little confused. Is it obvious to see why that's the expansion in conformal blocks? I think it just...
Not exactly, but
okay.
it is for the first term in the sense that when we expand at small z, so for example, the OP coefficient between the 2 O's and then the first composite, the scalar with n equals 0, is just the coefficient of z bar to the delta. So, at small z, this is just 2, right? So first of all, just expanding at small z, you see that there's an operator whose dimension is 2 delta. And up here, there's a delta, but the conformal blocks start in the small z limit with a dependence dimension minus spin over 2. So you see from this correlator that the leading guy, the 0, 0, 1, is just manifestly there because it's small z, you're just doing, a very simple expansion. Expanding at higher and higher orders, you see that you're just going to get powers of z and z bar shifted by integers. And slightly more care tells you that it's exactly this type of spectrum. Okay, so this was c to the 0, so no interactions. Obviously, things become more interesting at order 1 over C, where we have connected 4-point functions. And at order 1 over C, two things happen. Okay, so the first is that you have single trace exchanges, things like COO phi, and this would scale like 1 over root C canonically. For example, in a theory of a scalar coupled to gravity, you'd always have graviton exchange. And the double trace data gets corrected. So if we establish a shorthand A n comma L to be the squared OP coefficient of the external operators with the n comma L double trace, then this has a 1 over C expansion where the leading term is the generalized free field result, which I'm denoting with a 0 superscript, which just looks like a dot, but it's supposed to be a 0. And then there's going to be some 1 over C correction and higher orders likewise. And the dimensions also receive corrections. So part of what one is computing when you compute tree level correlators are these corrections. And this thing here can be interpreted as a binding energy in AdS of this 2-particle state due to the interactions, say, due to the gravitational interaction. Of course, there's also lots of interesting data in the single trace part. But given some single trace spectrum, so you have some Lagrangian, there's some exchanges, then you can extract from that the effect on these composite operators. So both of these things are what are being computed at tree level. There are two types of diagrams: contact diagrams and exchange diagrams. So the contact diagrams will be sort of also important for tomorrow's discussion. So let's draw this. So contact diagram means you have some quartic, in this case, a 4-point function, so quartic interaction in the bulk, something like 5 to the 4th. And, in view of time and interest, I'm not going to explicitly write out this thing in its full glory, but I think you already know basically how you compute this. You have some interaction point, which I'm going to put in orange. This has to get integrated over all of AdS, otherwise you don't get a conformally covariant object. And at each of these legs, you have a bulk to boundary propagator for the appropriate field. So you multiply these 4 propagators together, you integrate them over the common bulk point, and that defines the answer. Sometimes you can do the integral, sometimes you can't. In all cases, this is known as a D function, which is a function of the dimensions of the external operators. And when they're, say, integers, you can write this in terms of logs and dialogues. We're interested in the CFT decomposition of this thing. And sorry, to debug for tomorrow. So this decomposes into double trace operators only. So we're getting corrections to these OP coefficients from before and to these anomalous dimensions. A key point here is that these have support only on spins less than or equal to capital L, where L is, roughly speaking, the number of derivatives in the vertex divided by 2. So let me try to explain these features of contact diagrams. First, it sort of looks like there are no single trace exchanges, right? Because you just have some vertex and you have the external fields coming in. And so where would a single trace operator be? Right? It's not in the bulk, so there's not going to be one on the boundary. And that's a very heuristic way to think about this, but it's true. Less heuristic way, but still a useful mnemonic that can be made rigorous, is to think of cutting this diagram. So if you make a kind of cut like this, through these two lines, that corresponds to the exchange of a 1-2 double trace operator in the CFT side. And you can also cut this way. Whoa, that was not at all supposed to happen. You can also cut this way. And this gives you a 3-4 exchange on the CFT side. So drawing the diagrams this way, you can just sort of think of cutting them in different places, and that tells you what you get. This tells you what you get in an S-channel decomposition. If I cut this horizontally, then I'd get a 1-4 and a 2-3. And indeed, that's what would appear in a T-channel decomposition. 1-4 goes to 2-3. I get those composites appearing in that channel. This condition on the spins can be thought of in the following way. Unless you have derivatives of the vertex, then the vertex can't host the exchange of spinning operators. So imagine you sort of stretch the vertex out a little bit so that something is being exchanged as if you're integrating out some heavy particle. That thing has some spin. And so correspondingly on the CFT side, that bounds the spin of the operators that can be exchanged. This is the sort of intuitive way to think about it, and explicit calculation bears this out. So for
what
example,
do you mean by cutting?
By cutting, I mean, at this level, just drawing a line through the canonical way to draw this diagram and asking which of the bulk lines it crosses. And when it crosses, yeah, let me sort of, not sure. So when you make this kind of cut, this line crossed a 3 and a 4. Okay, and so that means that if I decompose the correlator in the S channel, there's going to be a 3-4 composite that's going to appear in the conformal block decomposition.
Is that supposed to be obvious? Like, I'm not seeing it that just because the line cuts 3 and 4.
It's not really supposed to be obvious. It's similar to things that are true about scattering amplitudes, but it's not really supposed to be obvious, and it's not indeed how that was first inferred. This notion was first sort of talked about by some papers by Fitzpatrick and Kaplan, and then in more recent years, you can systematize this. One can systematize this cutting procedure, generalize it to loops as well, where when you have loops in the bulk, you can ask what is being exchanged from the boundary, and the answer is given by this same kind of cutting mnemonic. But again, you know, what could the choices have been, right? So everything that could possibly be exchanged in the CFT side has to be made of the external operators. And if they were higher than double trace operators, that would actually violate the 1/c counting. You at a tree level for a 4-point function, those cannot appear. So it would have to be some double trace operators. And when you pick a direction, so, you know, if I wanted to decompose this thing in the S channel, which is 1-2 goes to 3-4, then, well, any operator appearing in that decomposition has to appear in the 1-2 OPE.
Yes.
And so we're looking at something in order 1/c. So what that means is that there's going to be some OP coefficient C, 1, 2, 5, C, 3, 4, 5. We want this to be order 1/c. And each of these corrections here is of order 1/c. So at one vertex, you need to have a correction. At the other vertex, you need to have a generalized free field result. And the only thing appearing in the 1-2 OPE in a generalized free field theory are composites of 1 and 2.
Yeah, okay, thanks.
So for example, if phi is a 1-2 composite, then on this side, you get a C to the 0 generalized free field OP coefficient. And over here, you get a 1/c correction. And likewise for 3-4 composites. So I think that's a fuller explanation.
Yeah, thanks.
Sure. Okay, so let me just say, in contrast, what exchange diagrams look like, because they are richer. And so we know how to draw this. Now we have two bulk points, and there is a field being exchanged. We have external propagators for these operators. And now we have a bulk-to-bulk propagator for some bulk field. Let's call it phi.
One question.
Yes.
for this contact diagram, does the D functions can be expanded in terms of your G functions? That is the conformal blocks.
Yes.
I mean, is it very trivial? I mean, is there any intuition what the coefficient should be, or how things look?
No, I would say there's no intuition, and one has to do computations. And over the years, there have been many computations trying to make that as efficient as possible.
Okay.
There, by this point, is certainly for fixed vertices with some fixed number of derivatives, it's very algorithmic. You can go and extract.
I'm saying you are writing this L less than equal to capital L, and all these informations are coming from that expansion, or it's just an extra assumption?
Oh, this L less than or equal to L thing?
Yes, capital L, yes.
Yeah, not an assumption. Not an assumption.
Oh,
so that is an output from computation, and I tried to sort of explain it physically. Yeah, thanks.
Thank you.
Good. So now for the exchange diagram, well, what is the CFT decomposition of this thing? Well, actually, it depends if you do it in the direct channel or in the cross channel. So here I've written an S channel exchange. So if I decompose this in what I call the direct channel, which here is the S channel. So just to make that totally clear with what we've been using before, if we decompose it into conformal blocks that look like this, then this includes the single trace exchange of the operator dual to phi, plus some double trace exchanges. And the spin of those double trace exchanges is bounded above by the spin of phi. So, right, it's what you'd expect. The single trace exchange would show up because I'm taking this bulk diagram. It looks like a conformal block. I mean, I've maybe done a trick of drawing, but you have some exchange in the bulk, and each bulk operator is dual to some boundary operator, and so that conformal block will appear when you decompose this thing. You also get some double trace pieces, and you can try to understand this by the sort of cutting mnemonic I said before. Right? If I cut down the middle, that corresponds to the CFT single trace exchange, and if I cut along the sides, then I get these other double trace pieces. You can also think of the fact that because these two bulk points are integrated over the full bulk, there'll be some region where they come close, and then it looks basically like a contact diagram. So you're going to get some double trace contributions from that region of integration. These are basically equivalent ways of thinking about it as far as I'm concerned. In the cross channel, though, so if I decompose this into T-channel blocks, which I'm free to try to do, then you just get double trace exchanges, and the spin is unbounded. You just get double trace exchanges because you're decomposing in cross-channel blocks, and so from that perspective, this bulk interaction looks like some non-local sum of contact diagrams, which are expanded in some funny direction, and so you don't get the single trace exchange when you expand it in the cross channel. But of course, you should remember that when you compute a full amplitude, you're summing over all channels. So if you have some identical 4-point function, identical operator 4-point function, there will be some channel where, say, the graviton is exchanged, or if there's a 3-point coupling, it'll be exchanged in some channel. So whatever channel you pick, you're going to get that exchange appearing. And of course, this thing is crossing symmetric, so it really doesn't matter what channel you pick. It never does. Okay, so this is a bit of the mechanics of these things. Let me make some comments about their essential features, more than what I've already said. So first, I've said this a few times, but it's important to write this. Any holographic correlator is a sum of Witten diagrams in all channels. So this is manifestly crossing symmetric. To me, this is actually an amazing thing about what AdS CFT tells us about strongly coupled CFTs, that there's some space, some way in which you can compute 4-point functions in which they're manifestly crossing symmetric and still also just a discrete sum over a bunch of exchanges. If you are just working on the CFT side, it is hard to see crossing symmetry a lot of the time if all you're given are some OP data, some low-lying operators in some channel. People have tried to work on the CFT side to implement manifestly crossing symmetric approaches to computing 4-point functions. This goes under the name more recently of the Mellin-Polyakov or Polyakov-Mellin Bootstrap. And the inspiration for that idea was, well, partly some old paper of Polyakov, but also the structure of holographic correlators. So the idea there was, can we use what we know about holographic correlators to rewrite 4-point functions of any CFT as sums of not conformal blocks, but actually crossing symmetric conformal blocks, which end up being essentially sums of exchange written diagrams. So work was put into trying to understand to what extent those form a basis and what one needs to do to tweak that. But putting that aside, just in the realm of holographic correlators, it's just pretty fascinating that this basic element of the holographic dictionary is telling us something which is at odds with the way you usually learn about CFT from the ground up. Not at odds with, but just at least, revealing of some interesting structure. We talked about the mnemonic of cutting. You might ask, what is the dual of a conformal block? This is something that I answered in some work from 2015. It's what's known as a geodesic Witten diagram. This was a paper with Elliot Hijano, Per Krause, and Rivers Snively. And what is a geodesic Witten diagram? It's an exchange diagram where instead of integrating these points over all of AdS, you integrate them over geodesics that connect the pairs of boundary points, which I've drawn here as these orange dashed lines. Okay. So you restrict the region of integration, and instead of computing this infinite sum of conformal blocks where you have a single trace exchange and all these double traces, this localizes that infinite sum onto just the single trace exchange. So this thing equals, so if we have some intermediate phi here, this equals a single conformal block for the exchange of the operator dual to phi. We felt this was important because in CFT, when you compute correlators, conformal blocks are essential. They get rid of the redundant symmetry information for you once and for all. And for many years in computing holographic correlators, that wasn't a core part of the way that was done. On the other hand, this observation ends up not being so critical for doing Bootstrap and holographic correlators, I should say. For example, if you're trying to decompose a sum of diagrams in all channels into a single channel in the CFT side, then this trick is not very helpful because you have diagrams you have to decompose in the cross channel, whereas the geodesic Witten diagram most naturally gives you a conformal block in the direct channel. And so
what does it mean by dual to conformal blocks? Like,
yeah, so good. So I mean, right. Dual is a little bit of a misnomer in the sense that these two objects are equal, provably equal. And so the word dual kind of invokes dynamics, but actually here we're just viewing the AdS side as a conformal computer, and you have an integral which is associated to this geodesic Witten diagram, and you can show that it's equal to the expression for a conformal block.
And I also one question that previously the Witten diagram was an integral over the full AdS volume. Now you are integrating over a line, right? Because it's a geodesic line. And you are saying that these two answers are the same.
I'm saying that when you do this geodesic integral, instead of the full AdS integral, you get a conformal block, a single conformal block.
One of the conformal blocks. Okay.
Yes.
Okay.
So one.
And how to select one of the conformal blocks? Like,
it's just the conformal block corresponding to the exchange of the operator dual to the exchange field in the bulk.
Okay. Okay. So yeah.
Yes. So this is really a kinematic equality, but it also allows you to decompose an exchange diagram extremely efficiently into direct channel blocks because you don't have to do any integrals. You put in the little work and then you show that the result is a sum of a bunch of these geodesic things, but then you, having identified those with conformal blocks, are done. You just read off the coefficients. But again, I don't want to overemphasize this. I think it's a useful entry in the dictionary and it was important to establish, but when you're trying to bootstrap the space of holographic theories, then there are better things to do.
Can I get double trace blocks from this construction as well?
Double twist blocks.
Like this will give me single trace block.
Well, so it doesn't matter how you think of this intermediate operator. It's just parameterized by some quantum numbers and away you go. But
okay,
for double twists, actually, there could be, so the answer is yes. If this operator has the dimensions corresponding to double twist, maybe the external operators, then this still works, except actually instead of a conformal block, you get a linear combination of the block and its derivative, because there are extra sort of singularities that appear in this integral. And so there are the usual kinds of subtleties, but they're all part of the package, and that's the way it should be. Yeah.
Yes, thanks.
Sure. Okay. So finally, the last comment before sort of turning to bootstrap approaches to computing holographic correlators, which I will only partly get to, and that's fine, is that it's important to summarize some of what we've said. The double trace data is fixed by the single trace data modulo contact terms. Right, so we have these two different types of diagrams. The contact diagrams give you double trace contributions. So do the single trace guys, in other words, the exchanges. And so modulo the contact diagrams, right, for every exchange diagram, there's some contribution to the double trace data. So this kind of fact that the double trace data is almost, or at least mostly, determined by the single trace data is especially clear in the Mellin formalism for computing holographic correlators. Perhaps we'll talk about this tomorrow. There's also a nice discussion of this in Joao Panadonis's TASI notes. And the contact terms are constrained. So one is not just free to add whatever contact terms one wants to some low energy effective action and be consistent with all principles of physics. We'll talk about that tomorrow too. Okay, so in the remaining time, I want to talk about some bootstrap approaches to computing correlators. And so, good. Perhaps we'll talk about two separate types of approaches, but perhaps not. Let's see. The first is to talk about a top-down case, so to speak, where we want to ask about strongly coupled 4D n equals 4 super Yang mills at leading order in the 1/C expansion, where we work at tree level in AdS. So, of course, this was one of the first things people wanted to do when AdS CFT was invented. There's a beautiful series of papers by Doker, Freeman, Rastelli, Mathur, Matusis, which computed some correlators of the stress tensor multiplet in n equals 4 super Yang mills from supergravity. So recall that this operator O2 from yesterday is the superconformal primary in the stress tensor multiplet. And the operators in the stress tensor multiplet are exactly those which are dual to the massless fields of AdS5 massless maximal supergravity. So what these authors did was, let's go over here. They computed it's the 4-point function of O2, which I'll write as 2, 2, 2, 2, at order 1 over C, which is tree level supergravity in AdS5. This was done in 1999 by brute force. The explicit result is, I mean, nice if you've had experience with holographic correlators, otherwise it's not the most enlightening thing. And since we have an eye toward what the conformal field theory content is of these kinds of computations, let me just quote the anomalous dimensions of these double trace operators of these 20 prime scalars. In particular, there are some unprotected composites of these two operators, these 20 primes. And so their anomalous dimensions, gamma and L at tree level, are equal to the following formula, which is useful to see. This is the closest we'll get to experiment in these lectures, so it's fun to write explicit formulas for real theories. And this is a pretty nice compact expression. Supersymmetry definitely helps, although it's not critical to the exact form of this. Note that for all n and L, whoops, these anomalous dimensions are negative. Okay. That actually turns out to be a general feature of anomalous dimensions in weakly coupled bulk theories with low spin matter, at least down to, say, scalar spin 0 or spin 2, where funny non-analytic things can happen in the spin. And so this was a brute force calculation, but so where does the bootstrap come in? That's where modern methods come into play. And actually, I'm going to quote 2 different papers by Leonardo Rastelli. So I guess he's to blame for a lot of the beautiful results here. So these results were reproduced and indeed significantly extended by the bootstrap. And here by bootstrap, I mean CFT computations, no computation of Witten diagrams, actual field theory calculations. So how is that possible? We're talking about strongly coupled n equals 4. Well, let me explain what I mean. Some information is being used that was learned from the bulk. Of course, retrospect is useful. But let me explain. So first, there's a nice paper by Beam, Rastelli, Van Rees that I referred to yesterday. And so what they did is they just looked at the n equals 4 crossing equation for the 4-point function of these 20 prime operators. They're not looking at any particular value of central charge. They're not sensitive to the exact value of the coupling because they are just looking at some 4-point function of some operator and asking how it behaves when you solve crossing. And so they are trying to solve the following problem, the general version of which I mentioned yesterday. They say we're looking at the OPE of 2 of these 20 prime operators. This includes the identity. And then there's going to be a bunch of protected operators, which I'm not writing because their dimensions are known and fixed. But there's going to be some sum over spins of some unprotected operators. And let's ask, can we bound the dimensions of the lightest operators appearing in this OPE of whatever low spins, 0, 2, 4? And well, the answer is yes, they could. And here's what they got. Okay. So I'm going to make a plot of 1 over C, where C is just an OPE coefficient appearing in this 4-point function. So it's a parameter that they can tune. And we're going to write the dimension delta L star, which are the dimensions of these light operators of spin L, lightest operators of spin L, minus their spins. So this is the twist of these low-lying operators. Now, let me just draw this for a second. Good, let's actually try this. Here's the value 4. Here's what they found. Near the origin in 1 over C. So here I'm plotting the first 3 spins. And of course, I'm exaggerating a bit to make a point, which I will explain shortly. So we want to look at this plot near infinite central charge. Okay, so near this region where they hit 4. So all these lines hit 4, and the slopes of these lines all match the formula that I gave on the top half of this slide, where you plug in n equals 0 to get the leading twist guy of spin L, and you plug in either L equals 0, 2, or 4. So the slopes match this holographic result at strong coupling for the pertinent values of L. And this is a pretty remarkable result because they did not put in strong coupling. They're just looking at the spectrum of this OPE, and they're looking at it as a function of central charge. And when you go to large central charge, well, what are these slopes? These are anomalous dimensions. And they find that the anomalous dimensions of their plot essentially saturate the known value as computed from actual supergravity. And just to clarify a point which I realize I've been unclear about, the plots they have are exclusion plots. Above these lines, the region is excluded. Okay. But it turns out that these lines, so these lines are the upper bound of what is allowed. So for example, for the scalar region, the dimension of the lightest scalar appearing in this OPE is somewhere in this blue region. And the slope over here turns out to be gamma 0, comma 0 as computed from supergravity. So the strongly coupled theory seems to saturate these bootstrap bounds, which were derived in complete generality. So this very much was not a priori guaranteed. And it tells you something which sort of you might have said was natural, that the strongly coupled theory seems to saturate the allowed values of parameters. But here they're deriving it just purely from rigorous crossing considerations. And well, deriving is not quite the right word, but showing experimentally that these values lie on their plot. Have any questions about this? Because I perhaps was a little elliptic in explaining the meaning of this plot. Maybe if there was one thing I would reemphasize in thinking back to the way I explained that, I would just say again, when you have a coupling, G Yang-Mills, that's not explicitly visible in your OPE decomposition. All the dimensions of operators would be functions of G in real life. But for some value of G, there's going to be some extremal value of G where the allowed largest dimension saturates some bound. Okay. And so you use the non-BPS data, this unprotected data, as a proxy for the dependence on the coupling. So you might ask, away from that boundary, how does the OPE data behave? And well, really, that's a very hard problem for the Bootstrap to access to sort of trace the conformal manifold in the presence of an exactly marginal coupling just by using the CFT data. But here, what is being shown is that at least at large C, the saturating value for these plots is that which was computed explicitly by supergravity, which is just really beautiful. Okay, and I've got about 3 or 4 minutes left or something. And so, okay, well, that's that. There was also a set of papers by Rastelli and Zhao, who actually went so far as to bootstrap the 4-point function at strong coupling without actually computing Witten diagrams. So they are writing down the explicit form of this correlator at tree level, which was computed by brute force in 1999 by summing Witten diagrams of the type I described earlier. So how do they do this? Well, so they used a bootstrap ansatz, where essentially they combined various consistency requirements that this correlator must impose, and then guessed and conjectured that there was a unique answer, which was later proven to be correct. I don't have the machinery to fully explain what they did, but let me just say what they imposed. Hopefully this will be of some value. So first, they said, okay, this must be crossing symmetric. Then they said, okay, it must be n equals 4 covariant. And in particular, in the decomposition of the 4-point function, it must include operators in the respective R symmetry channels. And some of those operators are protected, and those give some piece of the correlator, but it's the unprotected piece which they really wanted to bootstrap. And so here is where they got clever. So they used some knowledge of the single trace spectrum at large coupling. In particular, at large coupling n equals 4 super Yang-Mills, the single trace superconformal primaries are this operator O2 we've been talking about. And that's an infinite tower OP, which are half BPS superconformal primaries with dimension P in a particular representation of SU4. But in the O2 OPE, actually this is pretty much overkill. SU4 selection rules tell you that you just have the identity and then O2, and then multi-traces. No other single trace operators appear. There's some subtlety with O4, but anyway, no other single trace operators appear besides this. And so this strongly constrains the analytic structure of the correlator that one could possibly get. And finally, so they said that, well, in the flat space limit, this must behave in a certain way because we're interested in the correlator at strong coupling, where sort of we know in the back of our minds the bulk theory is two derivatives, and in the flat space limit, the scaling at high energies of this AdS amplitude so as to reproduce a flat space S matrix should have a certain behavior. This is where they encode the strong couplingness, because if the bulk theory had stringy corrections, then the flat space limit would also reflect that. So they are using some hindsight from what we know about strongly coupled n equals 4, but this turns out to be enough to guess the answer, and indeed to generalize this to an infinite set of correlators, P1, P2, P3, P4, at strong coupling and order 1 over C, where these P's represent these other half BPS operators in the spectrum of the n equals 4 theory. And these, except for low values of P, had not actually been computed in any other way. So this is quite a nice result. Okay, so we're out of time, but I hope to have conveyed what the Bootstrap could do, at least in part, in sort of allowing you to not have to compute Witten diagrams every time you want to learn something about a strongly coupled CFT. There is, of course, more to say, and well, I will say it, but tomorrow. So tomorrow we'll continue this. Perhaps I'll add some remarks that I was thinking about adding today. But we'll talk more about, so they continued for a little bit, perhaps, but then we'll talk more about the space of holographic CFTs. This will involve this HPPS paper in particular, which set off this whole subject, and whether and how one can constrain the single trace part of the spectrum, which is really kind of the Bootstrap question about what kinds of theories you can have. This will allow us to talk about the role of extra dimensions. And so let me just conclude with that for today. Thanks.
Thank you, Eric. Okay, let's see if there's some quick questions.
I have a question. It's basically what I asked before. I'm still a bit confused about how you can perform the OPE for a 4-point function in 2 different ways. Maybe it would help me if you could just draw an example of 4 points on the plane where you can perform the OP in 2 different ways, because I can't come up with an example.
So quintessential example is this. So this point 1/2 is halfway between the S channel and T channel origins.
Oh, so there you have a point that's 0, 1/2, 1, and infinity.
Yeah.
Okay,
so I can, so here I'm setting Z equal to Z bar equal to 1/2. And this is within this circle and also within this circle. Sorry, that shouldn't go out to infinity, of course, but it's supposed to be a unit circle. But yeah, that's the easiest.
Well, so here I can see
example.
how you can fuse 0 and 1/2 and 1 and infinity, but then I don't see any other way you can do it. Like you can do the OP between 0 and 1/2, and you can do the OP between 1 and infinity, because there it's within the radius of convergence. And then you can also do the OP between 1/2 and 1, but you wouldn't be able to fuse 0 and infinity because it crosses the operator insertion at 1 or at 1/2.
Well, infinity is kind of everywhere, right? I mean, when we say infinity,
if you
we
draw
really
this
mean
on a
the point
sphere,
at infinity.
Well, okay. Yeah, I mean, I was thinking of a point very far away, so at a very large
Then
radial
you could go around
distance.
the other way, or
Yeah, but then you can't do it the other way. Like
but you have a choice. So yeah, the sphere case, you can, in one channel you connect 0 and infinity one way around the sphere, and then the other channel you connect infinity to a point the other way around. Maybe I'm not being clear, but maybe we can talk about it later. I'd be happy.
Well, maybe to avoid this issue of infinity, we can just draw 4 points that aren't at infinity, because it should work, right? But I can't come up with a way to do it. We can talk about it later if you want to move on to another question.
Sure, but that might be better, but yeah.
Okay, thanks.
Thanks for the question.
More questions? Okay, if not, then let's thank Eric.